Okay, we now start the class. And do you have any question? Any question of last topic? Okay, we continue. No question. Okay, we continue the review of thermodynamics according to last session. We talk about first law of thermodynamics. First law of thermodynamics defined as a integral cycle of heat equal to integral cycle of work. We wrote the first law of thermodynamics for a cycle. Cycle has had two processes, A, B, and process A cycle with two processes A and C. So we wrote the first law of thermodynamics for both cycles. We inferred that parameter differential of heat minus differential of work are the same for all the paths between point state 1 and state 2. Finally we inferred that this quantity defined as energy. So if we integral of this equation between state 1 and state 2 means E2 minus E1 equal to Q process 1 to 2 minus work process 1 to 2. We talk about energy. Energy means sum of internal energy, kinetic energy, and potential energy. You are familiar with kinetic energy and potential energy from dynamics course in your bachelor period. But what is meaning of internal energy? Internal energy is combination of liquid state and vapor state. Internal energy equal to mass that shows with M cross U, means internal energy per kilogram, equal to mass of liquid cross internal energy of liquid plus mass of vapor cross internal energy of vapor. Finally, internal energy equal to internal energy of liquid plus X, that is quality of vapor. Quality means, according to definition of last section, mass of vapor divided by total mass cross internal energy UFG. So we solving a problem. Determine the property of following state. State 1, the temperature is 300 centigrade and internal energy equal to 2780 kilojoule per kilogram, and state 2, pressure equal to 2000 kilopascal and internal energy 2000 kilojoule per kilogram. So for state 1, if you refer to table B11 at end of the book, you find that at 300 centigrade, internal energy of vapor is 2563 kilojoule per kilogram. But what about U in case A? Case A is 2700. It's more than U of internal energy of vapor. So we are in superheat state. When we are in a superheat state, we should refer to table B13. Table B13. So if we refer to table B13, we see that internal energy of 2780 kilojoule per kilogram occur as 1600 kilopascal, and 1800 kilopascal at internal energy of 2776.8 kilojoule per kilogram. So the quantity of 2780 kilojoule per kilogram is between two numbers. So by interpolation we find that the pressure is 1648 kilopascal, and also with linear interpolation the specific volume equal to 0.1542 cubic meter per kilogram. It's an example for review. Any question about this example? Okay, part B is solved according to, you can find it in the below part of the A, case A. You can find the answer of it. Please solve this example yourself in the home. Other example. Consider a vessel of volume 5 cubic meter contain 0.05 cubic meter of saturated liquid and 4.95 cubic meter of saturated vapor at 0.1 megapascal. Heat is transferred to this vessel until the vessel filled with saturated vapor. Okay, we have two-phase flow and put heat to the system and finally have saturated vapor. Determine the heat transfer of the process. You can see the schematic of vessel to the figure. We are in point A. You can find it in TV diagram. In the below figure you find it that we are in state 1. State 1 means two-phase flow, and in constant volume process heat transfer to the vessel and the volume of vessel is constant. So heat transfer occurs in the constant volume process. So the process is continued to reach the point 2. At point 2, the water is in complete vapor. So we have a constant volume between state 1 and state 2. So we write the first law of thermodynamics for this process and neglect both potential energy variation and kinetic energy variation. So we finally find that first law of thermodynamics equal to Q between state 1 to 2 equal to internal energy at final state 2 minus internal energy at final state 1. So we can find the mass of the liquid from the volume of liquid and volume of vapor. So with mass of the liquid and mass of the vapor, we can write and determine the internal energy in state 1. State 1 is two-phase flow. One part for liquid, one part for vapor. So according to pressure of 0.1 megapascal, we find U in vapor, U in for liquid state and internal energy for vapor. So we can compute the internal energy in state 1 and state 2 quality is 100 equal to 1. So what is the mass of the vessel? 5 cubic meter. Okay, and what is the mass? We have in the state 1, we have two-phase flow. So one part is for mass of the liquid and one part is mass of the vapor. So we have the continuity of mass. So for 47.94 kilogram plus 2 minus 92 kilogram, we add to this term and find that the mass of the vessel is equal to 50.86 kilogram. So a specific volume equal to 5 divided by mass of complete mass or mass of the vapor and liquid. So the final specific volume equal to 0.09831 cubic meter per kilogram. So what we have in final state? A specific volume. So with this specific volume at the final state, pressure also increases. So the final state equal to nu index G, means a specific volume of vapor. So we find that at pressure of 2 minus 0.3 megapascal equal to this specific volume. So internal energy, specific internal energy determined at final state, and we can compute the internal energy at final state. So heat transfer between two processes can be computed by difference of U index 2 minus U index 1. This is other example. Any question? Extraction of this value from table, it is for actually we are in review. Okay, it's better you find and you try to find it yourself. If you have any problem, in the next section we can compute this value again. Any other question? Oh, I don't give you the value. You should extract it yourself. In the exam, I will give you the table, complete table, before the exam as a PDF file to you, and you can print it and use it in the exam. Any other question? Okay, we continue the lesson. We want to talk about other definition. Consider that we have a cylinder and piston. Consider that piston is in state 1. What happened if we put heat into the system? If we increase the heat and put heat into the system, the temperature of gas increases. But what about pressure? What do you think? Pressure is varying or not? We have a temperature variation in this example? What do you think? The pressure is constant in this problem. خب what equation do you want to talk about it, Kazem? Kazem, do you hear me? Which question do you talk about that? I don't know. First law or other equation? If you say me about that, we can talk about it. Okay, we continue, and you can ask the question in the class. Okay, consider that the pressure in this process is constant. Why? Because the mass of the piston is constant. So between state 1 and state 2, we have a constant pressure process. So how can we compute the work? Work in quasi-equilibrium process equal to integral between point 1 state 1 and state 2 of integral pressure cross differential volume. So the pressure is constant, so we can put the pressure outside the integral. So the work between state 1 and state 2 equal to pressure cross volume difference between state 1 and state 2. So we put this work in the first law of thermodynamics. So we computed the work between state 1 and state 2. So heat transfer between state 1 and state 2 equal to U2 minus U index 1 plus P2 cross V2 minus P1 cross P1. So we have a quantity of U plus pressure cross V. We define this quantity as enthalpy. So enthalpy is combination of internal energy and work of the flow. Work of the flow in what condition? Work of the flow at inlet and outlet of the system. You remember from the bachelor or basic thermodynamics that enthalpy equal to enthalpy of liquid plus quality cross HFG. Okay, this is definition of enthalpy. So we try to solve another example. Kazem, U means internal energy. Internal energy is a part of energy that depends on temperature of the matter. Okay, consider that you have a piece of iron. Okay, piece of iron. You put it in your hand. Its temperature is of temperature of environment. Consider, for example, 30 centigrade. What happened if we put this piece of iron on the fire? So if we put out this matter or iron on the fire, the temperature of the iron increases. So what is increases between two processes? Is internal energy of iron. This is the means of internal energy. Kazem, do you have any other question? Okay, we try to solve another example. In this example, a cylinder fitted with a piston has a volume of 1.1 cubic meter and contains of 0.5 kilogram of steam at 0.4 megapascal. Heat is transferred to the steam until the temperature increases to 300 centigrade. While the pressure is constant this process. For why? Because we have a cylinder and piston, and the mass of the piston didn't variate during this process. So this is a constant pressure process. We are in state 1, means that it's two-phase flow. We put heat into the system, or heat is transferred to the system until we reach to the state 2. You can find it in TV diagram. So we want to determine the heat transfer and work during this process. So this is a constant pressure process. So the quasi-equilibrium work equal to integral of state 1 and state 2 of P cross differential of volume. Pressure is constant, so the work is equal to pressure cross volume difference. Okay, and internal energy variation is computed by mass of the water cross difference between internal energy between state 2 and state 1. So the Q or heat transfer equal to mass cross enthalpy difference. So in state 1 we can compute the specific volume and the quality as state 1. What we know about state 1? We know that the pressure is 0.4 megapascal and volume of the cylinder and the germ of the vapor. So in state 1, specific volume equal to volume state 1 divided by mass. Volume state 1 equal to 0.1 cubic meter divided by 0.5 kilogram. So the specific volume is 0.2 cubic meter per kilogram. It's equal to, we have two-phase flow. Okay, we refer to table B12, and in 400 kilopascal or 0.4 megapascal, we see the mass of the specific volume in liquid state and specific volume in vapor state. So we write it and find the quality at state 1. So the quality as state 1 according to diagram can be determined. With this quality we also determine the enthalpy at state 1. Okay, we compute this in state 2. In state 2 the temperature is 300, and what about the pressure? Pressure is constant. If we refer to table B13, is superheat state. So we can compute the enthalpy at state 2. And we can compute also the heat transfer. Is equal to mass difference by enthalpy and is between state 2 and state 1. So the work can be determined is equal to mass cross pressure cross specific volume between state 2 and state 1. We also compute this heat transfer with internal energy. You can find it in this example. Is other path for the solving the problem. Any question? Okay, Kazem, why P1 equal to P2? Consider this example. We have a cylinder and piston. Okay, if we wrote the first law of Newton for this system, means that weight of the piston equal to pressure cross area of the piston. Okay, when the mass of the piston doesn't vary during this process, so the pressure also constant. So the process is constant pressure process. Yes. This is a constant pressure process. Any question? Okay, we continue the lesson. We want to talk about two other definition. Okay, consider the process, constant volume and constant pressure. We want to define two new definition: a specific heat at constant pressure and a specific heat at constant volume. Consider the first law of thermodynamics. It means that differential of heat equal to differential of internal energy plus differential of work. So if we have a quasi-equilibrium process, differential of Q equal to differential of internal energy plus pressure cross differential of V. So a specific volume defined as heat transfer means differential of Q divided by differential of T during constant volume process divided by mass. So in constant volume process, differential of V is 0 in the above equation. So differential of Q equal to differential of internal energy. Internal energy per mass is equal to a specific internal energy. So means differential of U divided by differential of T. In constant volume process, we define this quantity as a specific heat at constant volume. We write this as C index V. We also have another definition: a specific heat at constant pressure process. So what happened of differential of Q divided by differential of T during constant pressure process divided by M. So you remember that it from the several page ago that differential of Q during constant pressure process equal to differential of enthalpy. So differential of enthalpy divided by differential of temperature in constant pressure process equal to M. So the definition of enthalpy divided by M means a specific enthalpy. So differential of H divided by differential of T during constant pressure process defined as a specific heat as constant pressure. So for solid and liquids that volume is constant nearly, differential of H equal to differential of internal energy plus a specific volume divided by differential of pressure. So differential of H equal to differential of internal energy equal to a specific heat at a specific heat cross differential of temperature. So difference of enthalpy and difference in internal energy equal to a specific heat divided by cross by difference of temperature. So in liquid and solid and liquid, remember that from the physics and thermodynamics. In liquid and solid, constant pressure and constant volume of a specific heat is also equal to each other. So we don't talk about the specific heat at constant pressure or constant volume. Do you have any question of this part? Okay, we continue. Okay, we talk about heat transfer for solid and liquid, but what for gas? We consider the ideal gas process, means that pressure cross a specific volume equal to constant of gas cross temperature of the gas. You remember that internal energy of ideal gas is only depend of temperature. So a specific heat at constant volume equal to differential of U divided by differential of temperature in constant volume. Internal energy only depend on temperature. So a specific volume also depend on temperature. And what about enthalpy? Enthalpy equal to internal energy plus pressure cross constant volume. So according to ideal gas law, P cross a specific volume equal to constant of gas cross temperature. So When the internal energy is the only depend on temperature, so the enthalpy is also depend on temperature. So for ideal gas, internal energy and enthalpy is both of them depend only on temperature. Any question? Kazem, in the solid and liquid state, a specific volume is constant because many of the solids and liquid are incompressible. You know it from the fluid mechanics. Okay? Many liquid and solid are incompressible. So the specific volume or density is constant, and we can consider it at both specific volume and specific heat is the same for both states. But for ideal gas we have the other definition. So there is a variation or differences in constant pressure and constant volume process. Any other question? Okay, continue the lesson. So for ideal gas, a specific heat at constant pressure equal to differential of H divided by differential of T during constant pressure process. Also differential of H equal to a specific heat with we denote by P0 differential by T. So differential of H equal to differential of internal energy plus R cross differential of T. So we put for differential of enthalpy C index P0 cross by differential of T and equal to C index constant 0 cross differential of T plus R constant of gas cross differential of T. So if we divide both sides of this equation by dt, we find that C index P0 minus C index V0 equal to constant pressure of gas. So consider this diagram. This diagram shows the variation of C index P0 divided by R for different temperature. So for wide range of difference of temperature, the specific heat at constant volume and constant pressure, both of them are varying during this high temperature process. But if we only have a low range of variation, we can consider that a specific heat or for both of the P0 and V0 are constant. Any question? Yes, Kazem, after this session I will send you the PDF lecture completely, or I will send it to you. Don't worry about that. Any other question? Okay. So we want to continue the lesson with first law of thermodynamics for control volume process. You remember that we talked about difference between control mass and control volume. Control mass or system, there is no inlet and outlet of the system. System is isolated for entering and exciting of mass from the system. But in control volume, we have an inlet and outlet for the system. So the mass can be entered to the system and also can exit from the system. Okay, so for conservation of mass, we have a definition. Differential of mass of the control volume equal to add of all of the inlet mass minus adding of all the outlet mass. Okay, but in control mass we don't have this definition because any matter can't be entered to the system or can be exit to the system. So for the first law of thermodynamics, it's convert to dE index bond CV means control volume differential divided by dt differential of time equal to rate of heat transfer minus rate of the work plus mass flow cross energy that enters to the system minus mass flow cross energy that can exit to the system, exit of the control volume, plus work that is needed to put the mass into the system minus work that for outlet of the mass of the control volume. So differential of this system d E of control volume divided by T equal to rate of the heat of the control volume minus rate of the work done by the control volume plus mass flow rate of inlet cross EI means all of the energy of the mass plus PI cross VI minus m dot of the mass outlet of the system or exiting the system cross E index E plus PE cross VE. So if we put it into the system, we finally find that rate of the energy of control volume equal to rate of heat transfer minus rate of control volume work plus adding of internal enthalpy plus potential energy and kinetic energy between inlet and outlet. This is the first law of thermodynamics for the control volume process. Any question? Okay, we want to define process, steady state process. So in this process the control volume doesn't move in any coordinate. The mass at each point don't vary, it doesn't vary with time. As the mass that flows across the control volume surface, the mass flight at each point of the system don't vary with time. The rate at which work and heat cross the control volume surface remain constant. So for a steady state process, the mass of the system is constant. So the rate of the mass of the control volume equal to 0 and the rate of the internal energy of the control volume is 0. So adding of all the entering mass equal to adding of all outlet of the mass. And the first law is rate of the heat transfer equal to plus mass flow rate of inlet cross enthalpy plus kinetic energy plus potential energy equal to mass of the outlet of the system cross enthalpy plus potential energy and kinetic energy at the exit plus work done on the control volume of the system. So if we only have a one inlet and one outlet, is simplified according to this example, to this equation. Any other question? Okay. So you remember that many processes also in heat exchanger, nozzle, diffuser, throttle, turbine, compressor and pump, power plant, refrigerator, are all of them in the steady state process. So we continue the lesson in the tomorrow with transient process. If you have any question, I will answer to your question, and if you don't have any question, we can end the class. Any question?